All right, and so now in this example, in this particular problem right here, let's apply our understanding of the definite integral to find the work done, but the work done in stretching a spring right here. Okay, so it's another fascinating examples about how we can calculate work using the definite integral, but specifically we want to calculate work that's being done on stretching a spring. So before I even get into showing the wording description of the problem, let's try to understand the idea of any spring a little bit. Okay, so I mean, anyone knows what a spring is. Well, we got a spring, something that's in a coil shape, and so we can stretch it out, and then when we release it, it's going to naturally snap back to its natural length. Okay, so in the way how it is now, anytime you're looking at a spring, there's a phenomenon right here. I mean, there's a natural thing about the spring that any spring has its natural length. Okay, now I'm not talking about something like that, but the length is from here to here. Any spring has its own natural length. Let's say any length L, and then the same spring. You can see that the same spring, it's just the way the spring is. Any spring is, it stays in its natural length. But then if you want that to be longer, then you have to pull it out. Okay, we have to pull that spring out, and depending on the material that the spring is made of, then we're gonna have to exert even more force. See, like steel spring takes very large amount of force to pull it out, to stretch it out beyond its natural length, compared to rubber spring, right? It's just a little bit of force right there, and you can already stretch it so far beyond its natural length. So, but the idea, the fundamental here is that any spring must require a force to stretch it beyond its natural length right there. Okay, so this is the natural length, and of course I'm not an artist, so forgive me on that, but natural length was meant to be this L right here, but now we have stretched that an additional x distance. So it takes force to stretch the spring an additional x distance beyond its natural length. Okay? And then same thing, when the spring is in its natural length, you can also exert force to press it in. We're pushing it in. So force is causing a push or a pull. Okay? And so, just like that, with this spring right here, you can make it really tight in right here. Okay? And so, the natural length is here, but now we have to make it, this is the natural length, but now we have to make it shorter. Okay? So this is sort of like L minus X right here, but so actually we're pushing it, I'm drawing in the wrong direction, we're pushing it in some X distance. Okay? So doing any of that takes some amount of force right there. Okay? It takes some amount of force. And so now, before we, I also have to point out for you, you will have to experience on any spring on yourself a little bit. After this lesson, after this video, go ahead and have fun exploring any spring. I mean, grab an old piece of mattress, and inside of that mattress there must be some kind of spring coil. Okay, and I'm talking about grab an old piece of mattress, the kind of mattress where you're ready to dump that into a trash can or something like that, ready to dump that away. Take that spring out, okay, from where its natural length is, try to extend it out, and experiment that for yourself. Experience and experiment that for yourself. What I mean is, you see, so it stays whatever the coil spring is in whatever length it is. If you try to stretch it out, maybe it takes less force at first, but as you desire to stretch it out further, you're gonna really have to crank. What I'm trying to say now is that what I want to make anyone realize here is that the more we push it out beyond its natural length, the further we push it out, the more force we constantly have to keep exerting, the more force that we have to keep continuously exerting, more force required to keep it even further out and further out. Okay, so the larger this x is, because remember x is the amount of either you stretch it out stretch it out or compress it in. So the more x, the more force you need. Okay, so it's another situation here where you have to keep changing your force as you desire another distance. And hey, wait a minute, x, we're pushing it in or we're pulling it out in a distance x. All right, in a distance x. So there's some work done. I mean, there will be eventually some work done here. We gotta exert some force, stretch it out, okay, from beyond its natural length. So it gets stretched out in a certain distance. So work done in a distance. So force exerted to get work done in a distance. That's why now we're about to calculating work right there. So now, before I even get into the little bit more, before I get into that the wording description of the problem, but there's a law very well known in physics course. It's called Hooke's law. Okay, it's all credit to that mathematician and physicist Hooke right there. Hooke's law stated that the amount of force as a function depends on x, how far we stretch it beyond its natural length, okay, or how far we compress that on its natural length. It's found by, it's simply the amount of force there is just simply a constant k times x, okay, and this is on standard units. On standard units, this is Newton, and this is on standard units right here is meter, okay, but then force here is in Newton. All right, but then units shouldn't be a matter here, because for outside of the metric system and the SI units right here, there's also the kind of units that the Americans are using. They go with foot pounds and pounds right there, and feet and foot. Okay, and so units shouldn't matter. But Hooke's law stated that it needs a constant. So this is called a spring constant. This k right here is a spring constant. Any spring has its own constant. Okay, so now on whatever spring this is, depending on its constant, depending on its material, it has a different spring constant. But now, if you want to stretch that to a distance x beyond its length, right there, its natural length, the length that it stays at rest right there. So if we want to pull it out or push it in, okay. So Hooke's law is also for pushing in, or I mean pressing it in or stretching it out, okay. But that amount of force there is going to be k times x, and k is a spring constant. So every spring has its own spring constant depending on what kind of material it is. Okay? So that's Hooke's law. So now clearly, and at this point, without having any specific spring material in mind, then we have to leave this k. We have no better choice rather than leaving that as a constant k right here, but it's a constant coefficient now. And depending on the force amount is a function. It's now a quantity that's dependent on how far we want to stretch or how far we want to compress that. All right. So now it's another situation where we have changing force. Okay. So now in that way, let's bring that into our actual problem here. So now let's get started with one problem where we want to find work done on a spring. And immediately after this, still within the same video lesson here, we will be looking into another one. So here we can call that part A of our example here, or a part A of our application here. So now we're looking at a force of 5 pounds is required to hold a spring stretched 0.3 feet beyond its natural length. How much work in foot-pounds is done in stretching the spring from its natural length to 0.8 feet beyond its natural length? Okay. So now, this problem here, one thing that caught my attention, I introduced briefly before we got into any of these problems that newtons and length are usually expressed in, force and length are usually expressed in newton and meters for units like that. But in some circumstances, we also express that in terms of pounds and foot-pounds. So pound is for force, foot-pounds is for work, and then the feet and foot or for length here, and all that work law will work the same too. Okay, so this problem is expressing the problem in the American convention right here. So these are the American measuring system. So now what caught my attention is that a force of 5 pounds, okay, is required to hold a spring stretch. So now don't mistake that this is the natural length. This is not the natural length. This is only being stretched 0.3 feet. 0.3 feet beyond its natural length. So that means if we want to stretch the spring, whatever spring that is, 0.3 feet beyond its natural length, then it's going to take 5 pounds to hold that spring stretched out that far. And then the question, yes, as how it is, the question is asking how much work in foot-pounds that must be done, right, in stretching the spring from its natural length to 0.8 feet beyond its length, like that. So the question right as of now, the question is not too important yet, but let's try to understand about the spring a little bit. So I talked about any spring has a spring constant because it depends on what kind of material it is. So for this spring, in this problem, we could particularly doing then whatever natural length that is of the spring, the length in its natural state, we don't know that length. Let's call that L. And actually, as I'm going through the problem, you will realize that the natural length is not even an important matter here. But so here's the thing. This problem is telling us that from the natural length, if we stretch, I'm trying my best here. So if we try to stretch the, okay. So now I'm trying to draw that stretch version of the spring right here. So this is the same natural length right here, but if we're stretching it out, a distance 0.3 feet in my drawing. Okay, that's according to the description of the problem. So if we want to stretch this same spring, whatever that material is, if we stretch it out 0.3 feet, okay, then to do that, we need a force of, so our force here is 5 pounds. That's the force being 5 pounds. We need that force to stretch that spring out and hold it at 0.3 feet beyond, or 0.3 feet longer than its natural length. Okay, we still don't know what the natural length of the spring is, and as a matter of fact, it's not important. We don't know what kind of spring that is. Is that a steel spring, or is that a rubber spring, or is that a whatever spring that is? We don't know yet. Everything we know at this point are these two given value, and one more piece of information. Hooke's law says the amount of force. So we know that when we specifically stretch it out to 0.3 feet beyond its natural length, then it takes 5 pounds of force. But generally, according to Hooke's law, then the amount of force to stretch or compress that at any distance beyond its length, beyond its natural length, is going to be K times X. And here, in case I forgot to mention in the general discussion about the spring right before we got into doing the actual problem here, then I have to also emphasize the spring constant is always a positive constant. Okay, so that takes away the worry about signs or anything like that. But so now, this is the general description of how much force that we want to maintain the spring stretch or compress at some x distance away from its natural length. And so in that case right here, now we know that it's going to be 5 pounds. It's going to be 5 pounds to be, the force is going to be 5 pounds. That's why I'm writing 5 equals force. But the force to stretch the spring out at 0.3 feet beyond its length, because the x here, now I'm substituting 0.3 into my function. So force is a function of x representing the distance beyond its length. Okay, and so that means 5 equals F at 0.3. But F at 0.3 is the same as K times 0.3. So on the right hand side of this equation, it's all about the Hooke's law that we're doing right there. So 5 is the amount of force that's required, equals, according to Hooke's law, 0.3 times the spring constant. So from that, I am going to solve for K. That's my key right there, to find out what spring constant I have, and really that's all we need. Spring constant now will equal 5 divided by 0.3. Okay, and in this case specifically, allow me to use a fraction. But so spring constant, I found out it is going to be a 50 over 3 right there. Okay, 50 over 3. So that's my spring constant. And so now, once I've had the spring constant and have a little better understanding about the spring, now let's look back into the wording description of the problem one more time. So now the question is getting directly into how much work in foot-pounds is done in stretching the spring from its natural length. Okay, from its natural length to 8 feet, to 0.8 feet beyond its natural length. Okay, and so now how much work? The idea we want to realize now is that the path from stretching it out from natural length and stretching it out some x distance, that's your path there of stretching it. That's a distance to exert that amount of force. And just throughout that distance right here, you have so much force changing. So now, allow me to create a brand new structure, right here, a brand new picture on the other board. Actually, I don't need to. Just here, let me just simply change that. So we just now found that the spring constant is that's how we solve for spring constant. But now back to the picture itself. Think about natural length is here. X equals 0 is here. And we want to stretch it out to x equals 0.8. So we want to stretch it out a total distance of 0.8. Okay, so that's our distance. And so there's force. There's force to make this thing stretched out. Okay, to make the spring stretched out. So there's a distance and there's force. So that's why it makes sense that the question is asking for how much total work. Okay, but now I have to remind anyone viewing this lesson. Total work here is done by what? Accumulating all little work amounts. Accumulating all the little work amounts. Again, as a reminder, now I'm going to swing to the other board right there. So, total work. Okay, total work equals accumulation. So first of all, we have to find all the little work amounts. Okay, and accumulating all of those little work amounts from a start to an end. Okay, or specifically, according to many textbooks, little work amounts is dW from start to an end. Okay. That's how we are going to obtain our total work amount. Okay, so now just that distance that we are stretching our spring out, then okay, from natural length. So when the spring stays at natural length, this means we stretch at 0 distance. And then now I'm going to stretch it out to some, this is here to some x equals 0.8 length right here, beyond its natural length right here. So that means in that distance that we're stretching the spring out, in that distance where I stretch the spring, then throughout so many or infinitely many instances along the way right here, then we have to change a lot of forces. Because recall from the other board, when it was only a 0.3, then we had some force. It was 5 pounds, and then when it goes a little bit more than 0.3, then it has to be a different force amount. Okay? And so in that way, generally speaking, we think about, again, that force is changing continuously here. And then we come up with that strategy that we think about the whole path here from no stretch, natural state, to completely stretched out at 0.8 feet beyond its natural length. We can divide that into so many sub-little distances. So from here, from each one of these right here, and the more we divide into the sub-distances, then the smaller each of these little distances. And so, but each of these is a little change in the length beyond natural state. So I call it, it's a dx expression. So this is a little distance. We got a whole bunch of little distance, and they keep getting smaller as we desire more little subsection. And on each of those little subsection right there as a dx. Okay. So this is a little distance. And then force, we multiply with force there, and now force is found. The force to stretch the constant, to stretch the spring there is going to be now 50/3 times x. This is our final conclusion about the spring, according to Hooke's law. So we found the spring constant here specifically is 50/3. So the force generally at any point to stretch the spring to any x distance beyond its length is going to be, for this spring, whatever material that is, 50/3 times x. And that is why now realizing that we have a continuously changing force right here, I must multiply that force with all of the, on any infinitesimally small change in distance, any infinitesimally small distance right here, I'm going to multiply that with the force. And so you have to understand again, the idea here, this dx, this distance here is infinitesimally small, only a slight bit change right there. It's already, that's already having some work done on that. So this is some little work amount right there. Okay, and it's, the change here is so small to the point that the force, we got to take that change here, that distance here is so small so that we won't realize too much difference in the force here. So that no matter if, so that, you know, the force here can come out just like, you know, how much force that is right at that instant when x hits to whatever specific length beyond the natural length. And so now all I say again, this is force, the little amount of force. Okay, this is force, but I'm multiplying that with distance, little distance. And so now with little, this is a little amount of force, dw right here. That's my dw. So now, according to the fundamental I explained earlier, we want to accumulate all of these little work amounts. So that means I'm going to accumulate all of that. So now I have 50/3x dx. We want to accumulate, and the picture here is making it clear. We're accumulating from no stretch to the most at the end of our problem here when x equals 0.8. So now I'm going from 0 to 2.8. That completes my integral to calculate the total work amount right here. Okay, and so now again with this problem right here, we specifically require that, you know, anyone viewing this video lesson here have to watch this after you know what the fundamental theorem of calculus is, because that is what I'm about to use to find the actual answer of this definite integral. So again, this is little work amounts. Accumulating all of those little work amounts, it's going to get us the total work amount right here. Okay, and so now at this point right here, we are pretty ready for that. Fundamental theorem of calculus says we're going to go ahead and find just the antiderivative of this 50/3x right here, which gives me 25/3x squared right there. And I am going to evaluate that antiderivative from 0 to 2.8. Okay, from 0 to 0.8. And that means a little more mathematical expression right here, a little further mathematical work, and you can see that I don't need to spend too much space on my board here to do the calculation. Okay, and so now it's going to be 25/3 times a 0.8 square. Okay, and then that's the antiderivative substituted or evaluated at 0.8. And then the other part, when we're evaluating 0 into the antiderivative, it's just a zero out term like that. Okay, and so the final answer here will quickly come out to be in fraction. Okay, 16/3. Okay, and the units for this work right here, foot-pound. right? So foot-pounds, or I can just write that up here, foot-pounds. That's the units for this, instead of Newton, because again, this problem here, it has all that fundamentals about a spring, and about all the fundamentals about work and force, how they're related, but we measure everything in terms of the American standard right here, the American units right here. And I'm talking about the kind of units that are being used in the United States of America. Okay? And so that's our final amount of work for that. All right? So again, this is a problem where it emphasizes what I demonstrated earlier in the general discussion lecture, that we have the kind of, it's a path. It's a one path. As we're on our path to extend the spring longer from its natural length, then the force, the amount of force changing. See, force here is different with that force there, or the force at that point is different there. So at every single different point on that, we have a different amount of force. Okay, so just relating this to that, back to that story when I brought up in the discussion about the general discussion about the work right here, then we're talking about, hey, imagine there's a man trying to push that box, and then there's a hidden secret man trying to keep adding more the mass into that box, so that it's getting heavier. And so it's the similar situation here. As we pushing that along the path here, we have to exert more force. We have to keep pushing more force to make it. But in this case, there is no secret man, secret mean man that doing that. It's just the nature of the spring itself. It gets heavier as we're attempting to pull it out further and further beyond its natural length like that. Okay, and so the strategy here is we're breaking it down, the entire path, we break it down into multiple little subsections of distances. And the more we break it down, the better accuracy we get, and then we're accumulating all of those little work amounts together. So on each section here, there's a little work amount. That's how I'm seeing it. Okay. All right, so then in that way right here, still we're working with spring. Let's see how we can apply our understanding of definite integral into working with the work apply on a spring right here. Then here, let's call that part B of our example. That we're still working with a spring, but let me change the situation to something else different right here. So, and here in this problem, if we can quickly read through, then I'm using the problem here is going with the international convention, where work is measured in joules, and then force is measured in newtons, and distances are measured in meters, and then here the problem is in centimeters. Okay, and so now let's spend some time reading the wording description of this part B right here. The work of 5 joules. A work of 5 joules is done in stretching a spring from its natural length to 16 centimeters beyond its natural length. So from learning from part A, then we already had some experience. So it takes some force, but now it actually says the work is 5 joules is done by stretching a spring from its natural length to 16 centimeters beyond its natural length. The question here really is asking for what is the force in newtons that holds a spring stretched at the same distance. Okay, at the same distance being 16 centimeters. Okay, and so from what I was extracting out the information here, Hooke's law always say that the force needed, but here I'm talking about the force. The problem was saying about the work, we will get to that. But the force is always the force to stretch a spring from its natural length to be f of x equals some kx, and we have not even found our spring constant yet. And of course, this is part B of the example that we're doing. So it's a different spring, different material. So I have to restart from scratch finding that spring constant right here. But generally, according to Hooke's law, any force, the amount of force to generally at any point, right, to stretch out a spring beyond its natural length by some x distance is going to be k times x. Okay? And so now in that way, from our understanding, then so work, drawing a little bit of experience from part A right there, then we know that work has to be done as following. Total work of stretching it out to be accumulation So little work amount is going to be kx, even though we still don't know what k is. Kx times dx, because I described that situation earlier in part A that, as we stretch the spring from natural length, okay, and now this is natural length of the spring, and now the same spring, if we want to stretch it out like this far out, right, some x distance beyond its natural length, this is the x distance right here. And so in that x distance beyond its natural length, we can try to break it down into infinitely many sub-distances. Instead of saying sub-intervals, it's better, it's more appropriate now to say we're breaking that total distance of stretching into sub-distances. So we break that into we underwent a first sub-distance, and then another one, and then another one, and each of those we keep letting it become infinitesimally small. Okay, and so that's why this expression generally represents the amount of, or the little work amount. So total work here is the accumulation. Okay, so from the general understanding, and then from what I have explained in part A of the example. And so now it's apparently clear that just like the experience we've drawn out from part A, and here we're stretching it out from 0 to 16, but 16 centimeters. But the x here, when we're going with the international convention, and x is in meters. Okay, but now our problem is in centimeters, so we have to write this as 0.16, because we have to ensure, when we're using the international unit system for work and force and all that, where things are going in joules and newtons, then the distance is in meters. So when we're working with the centimeters like this, then we have to express 16 centimeters at 0.16 meters. Okay, so now we know that according to the problem, work of 5 joules is done. So when we're stretching it to 16 from its natural length to 16 centimeters beyond its natural length like that, and we need to take a work of 5 joules to get it done. So it takes a work of 5 joules to get it done. And so now in this way right here, I know that in this expression, I know that all of that here after accumulating, so the total work to get it stretched out from 16, stretched out to 16 centimeters beyond its length has to be 5 joules. So 5 equals the integral from 0 to 0.16 kx dx. Okay, and we have our choice to bring out that constant k right here, but it's not too important. But now at least we have an equation that 5 on the left-hand side must equal, now fundamental theorem of calculus here tells us that we can, with this integral right here, with this definite integral, we can go ahead and find the antiderivative, which gives us 1/2 kx squared. You see, 2 different letters right here, in case anyone is inexperienced. You see, we're starting to be exposed to multiple letters here. Which one is the main variable to take the antiderivative? The x here has to be the one, because our expression here is the dx expression. Okay, so taking the antiderivative here in respect to x, it's 1/2 k times x squared. But fundamental theorem of calculus say we need to evaluate this right-hand side antiderivative as from 0 to 0.16. That means we produce the next equation as following. 5 on the left-hand side, nothing be done much. 1/2 times k times 0.16 square, okay, and then minus all of the 0 out here, because one substituted this 0 into that expression, it's a 0 out. And so now look at this expression. All of a sudden we realize, allow me to write it down on the other space right there. All of a sudden we realize that we have an equation. 5 equals k over 2 times 0.16 all squared. Now we can use this relationship right here to solve for our value of k. And so in this way, I'm multiplying both sides by 2 and then divided by the square of 0.16. So k should equal whatever comes out from 10 divided by 0.16 all squared there. Okay? So in that way, my spring constant now is found to be 0.625. It's a positive value for spring constant. All right. So we arrive at the spring constant, but let's one more time swing back and look at the wording description. The problem wants us to find how much force. So what is the force in newtons that holds the spring stretch at the same distance? Okay, so the same distance. What distance? If we stretch the spring, if we stretch the spring 16 centimeters, right there, how much force does it take? Okay, how much force do we need to exert on the spring ends right there to pull it out? Okay, and Hooke's law is stated right here. And now, by the way, back to this Hooke's law right here, then we are clear that according to Hooke's law here, then f of x, the force that's needed to pull that out, to stretch it out, is going to be, has to be 390.625 x. Okay, the distance in x multiplied with 390.625 like that. Okay, and so in that way, yes, I'm concluding with the spring constant found right here. I know that according to Hooke's law, it's 390.625 x. So that means now at 16 centimeters, okay, or exactly 0.16. Because recall again, when we're using the international units for the spring, for the distance, then it's meter, okay, and force is in newtons, and then the work is in the joules. And so in that way, I am going to substitute. The problem gives us 16 centimeters. We need to think of that as 0.16 meters. So in that way, at x equals 0.16 meters, then the amount of force that needs to pull it that far stretched is going to be capital F at 0.16. Okay, this is the force function according to Hooke's law right here. And so now that is going to give me 390.625, and I'm multiplying that with 0.16, and that now gives me my final calculation came out to be 62.5, and this is in international units right here. So, and it's force, so it's newtons, 62.5 newtons right here. And that's how we've learned another problem that directly work with the work applied on a work that's being done to a spring right here, the amount of work being done on a spring. But it's the problem started out by giving us how much work being done on that spring to stretch it out to a certain length beyond its natural length, and then we go from there to identify the spring constant, and then from that we're able to arrive at our state law function right here. The Hooke's law function. Okay, so and so from there, from after having k right here, we're gonna be able to derive our Hooke's law function right here to determine how much force in general to pull the spring out, and then from there we should be able to identify how much force necessary to pull that spring to stretch out at 16 centimeters. Okay.